Okay, let's continue with the motion of a particle in simple harmonic motion. We saw earlier that the acceleration of a particle in simple harmonic motion can be written as follows. Acceleration A along the x-axis is equal to minus k over m x, where k is the spring constant for the spring that causes oscillation, m is the mass of the particle, and notice that this mass is in kilograms, of course, and spring constant is going to be in newtons per meter. We already know from Newton's second law that acceleration along the x-axis can be written as follows. And therefore, we can say that d squared x dt squared is equal to minus k over m times x. We can make a change where we can choose a constant, and we call it omega squared, and that will be equal to k over m. So we can rewrite d squared x dt squared to be equal to minus omega squared x. This equation that we have now is called the second order differential equation. We can rewrite it as d squared x dt squared plus omega squared x equals 0. And we can find a solution to this second order differential equation by looking at the trigonometric functions. And because we know the object is in simple harmonic motion, we can expect that a trigonometric function of sine and cosine will exhibit this type of behavior. And so we can use this as a solution to the differential equation. So we can propose a solution as follows, where we can say that x of t is equal to a cosine omega t plus phi, and we can say a is the amplitude of the motion. Amplitude, of course, is in meters, and omega is angular frequency, and omega can also be written as 2 pi f, where f is frequency in hertz, and angular frequency, of course, is also in hertz. And then we have phi, which is the phase angle, and t, of course, is time in seconds. So these quantities a, omega, and t, a, omega, and phi. So these quantities a, omega, and phi are all constants, and we can show that this solution satisfies the differential equation by first trying it out. And the way we try it out is to just take the derivative. So we start off with x of t equals a cosine omega t plus phi, and the first derivative, the x of t dt, can be written as a d dt cosine omega t plus phi, which then can be written as minus omega a sine omega t plus phi. And then the second derivative, d squared x of t dt squared, then becomes minus omega a d dt sine omega t plus phi, and this can be written as minus omega squared a cosine omega t plus phi. From that, we can now go to our equation, our differential equation, and substitute that into that differential equation. So we can say that comparing the second derivative, we have the following: d squared x dt squared can be written as minus omega squared a cosine omega t plus phi. And if we just compare this to our original differential equation, our differential equation was written as d squared x dt squared, which was equal to minus omega squared x, where x was equal to a cosine omega t plus phi. And so by looking at it, we can see that this solution satisfies our differential equation. Note that omega squared is equal to k over m. Therefore, we can say that omega angular frequency is equal to the square root of k over m. We can now find a mathematical expression for the period of the motion. And the period is the time required for the particle to go through one complete oscillation. This time is of course measured in seconds. After the particle goes through one complete oscillation, its positions x of t and velocity v of t will be the same at a particular time t as if it had gone through a time t plus the one period. So we can say that after one complete oscillation, now because the phase increases by 2 pi radians in a time interval of t, we can write that omega of t plus big T, the capitalized T, plus the phase minus omega of t, so omega t plus phi should be equal to 2 pi. So what this tells us is that omega t plus omega capitalized T plus phi minus omega t minus phi is equal to 2 pi. So simplifying leads to omega plus times uppercase T equals 2 pi. So the time period T is equal to 2 pi divided by omega. Yes, I'll put a box around it. And we already know that the frequency is the inverse of the period. We have F equals omega over 2 pi. We already mentioned earlier that omega is the angular frequency. So we can say that now we can write omega, which is our angular frequency, as follows. Omega is equal to 2 pi times F, just from the formula above. So we can write that the frequency of oscillation is equal to omega divided by 2 pi. And so let me start over. Because we know that F, the frequency, is equal to omega over 2 pi, we can write F equals 1 over 2 pi, and we know omega is equal to the square root of k over m. So we can write this as the frequency of oscillation for a particle in simple harmonic motion. The question next then is, what is the velocity of the particle in simple harmonic motion? Note that since the particle in simple harmonic motion, its velocity is going to oscillate along with its position. So recall that we already have that the position of the particle in simple harmonic motion can be described as a cosine of omega t plus phi. And this shows that the particle is an oscillatory motion, meaning that its position changes along a cosine curve. So, but to find velocity v of t, we take a derivative of x of t. And so we say d dt x of t is equal to v of t, and this can be written as minus omega a sine omega t plus phi. So that's the velocity of a particle in simple harmonic motion. And we've already calculated acceleration earlier. So now let's look at what happens for the maximum velocity. Let's call it v max. So from looking at our velocity function, v of t equals minus omega a sine omega t plus phi. We know that sine 90 is equal to 1, so meaning that the function would be a maximum when omega t plus phi is equal to 90 degrees. So this tells us that the extreme values of our velocity functions will occur at plus minus 1 along the angle. That is when the cosine and sine functions lie at plus minus 1. So our maximum velocity can be written as v max will be equal to plus minus omega a. In the same way, we can find our maximum acceleration, let's call it A max, by analyzing our acceleration formula. And our acceleration formula was A equals d squared x dt squared, and that was written as minus omega squared A cosine omega t plus phi. Again, I've already mentioned that our maximum values occur at plus minus A. Our maximum values occur at plus minus 1 because of the oscillation of the sine and cosine function. So we know that the maximum values occur at plus minus 1 for the sine and cosine functions. So we can say that A max is equal to plus minus omega squared A. So let me just add here that V max is equal to omega A. And the term here where I have plus minus A just tells us that the maximum velocity occurs at plus minus A. So I'll just put here occurs at plus minus A omega A. And in the same way, we can say that A max occurs at plus minus omega squared A, and A max itself, we can take an A max to be equal to omega squared A, which can be written as K over M times A. Okay, so we can now plot the graphs of the displacement, velocity, and acceleration for a particle in simple harmonic motion. I'm using SHM for simple harmonic motion. So let's plot x of t first. Because the displacement is a cosine graph based upon our solution to the differential equation, we can start off this way as a cosine graph. This is A, and this is minus A. And we can also plot the velocity graph, V of t. The velocity is a sine graph, so let's plot it this way. Where this is your V max, this is minus V max. And you can see that the maximum velocity occurs when the displacement is at 0 position. Redraw it to scale if you like. And then we can also draw the acceleration. So let's do A of t. So this is your A max. And this is minus A max. So those are your graphs for displacement, velocity, and acceleration for an object in simple harmonic motion. Let's do a quick example of an object in simple harmonic motion. Let's say a 100 gram block. Okay, let's start over. A 150 gram block is connected to a spring with spring constant. Let's say the spring constant is 4 newtons per meter and is free to oscillate on a horizontal frictionless surface. Let's say, suppose the block is displaced 4 centimeters from equilibrium and released from rest. Find A, period of motion, B, maximum speed of the block, C, maximum acceleration, and let's try D, an expression for the position, velocity, and acceleration. Let's look at the solutions next. We start off with solution A. We want to find the period of the motion. We know that the period t is equal to 2 pi divided by omega, where omega is equal to the square root of spring constant divided by mass. We know the spring constant K is equal to 4 newtons per meter. And we also know that the mass of the block is 150 grams. We can write that in kilograms as 0.15 kilograms. So from that, we should be able to calculate the period. So first of all, let's calculate angular frequency. This is given by the square root of 4 newtons per meter divided by the mass, which is 0.15 kilograms. And that gives us, we have to do a calculation, that gives us 5.16 radians per second, or you can just write 5.16 per second. This is a frequency unit. 5.16 per second is the same as 5.16 hertz. From that, we can find the period t by just dividing by 2 pi. So we can have 2 times 3.142 divided by 5.16, and that should give us 1.21 seconds. And then for B, we want to find the maximum speed of the block. We know from our formula that V max is given by omega A. So we know omega is equal to the angular frequency 5.16 per second, and amplitude A is the maximum displacement from equilibrium. The maximum displacement in this question is 4 centimeters from equilibrium, so we write 0.04 meters, and so V max can be written as 5.16 per second multiplied by 0.04 meters, and that should give us a result, so 0.206. And then C, we want to find our maximum acceleration. Maximum acceleration was given as A max equals omega squared A. So we can just square the omega, 5.16 squared, and multiply that by 0.04. That's 1.065 meters per second squared. And then for D, to find an expression for the position, velocity, and acceleration, we know that in general, for our simple harmonic motion, we know that x of t, the displacement, is given by A cosine omega t plus phi. Let's first find the phase from the conditions given. The initial conditions are that the maximum displacement x is equal to A at an initial time t equals 0, since it starts from rest, and we set the time t equals 0. So from that, x of 0 is equal to A cosine omega times 0 plus phi. So x of 0 is equal to A cosine phi. Because we know that the maximum amplitude is A, because we know that the maximum amplitude at time t equals 0 is A, so we are saying that x of 0 is equal to A cosine phi, which is equal to A. This implies that phi is equal to 0. So in order for our maximum amplitude at time t equals 0 to be A, it means that the phase angle phi should be 0, so that cosine 0 should be equal to 1. So we are saying phi is equal to 0. So we found our phi value, and that's 0. So to start off, we can just now say that with our displacement x of t, now plug in what we know. We know first of all that A is equal to 4 centimeters. We also know that omega is equal to 5.16 rads per second, which we calculated. And so we can write x of t, which we know is A cosine omega t, to be equal to 0.04 cosine 5.16 t. So this is your displacement x of t. Note that the amplitude is in meters, so I change from 4 centimeters to meters, which is 0.04 meters. So that's your displacement x of t. And then for velocity v of t was equal to minus omega a sine omega t plus phi in general. We already know that phi is equal to 0. We know that a is equal to 0.04 meters, and we know omega to be 5.16 per second. So we can plug this in to get our velocity function, or velocity expression v of t, which can be written as minus 5.16 times 0.04 sine 5.16 t. So we have 5.16 times 0.04. That gives us 0.206 sine 5.16 t. So this is your v of t, and it's a negative. Put a negative in front of it. And then the last expression is for a of t. We know a of t is equal to minus omega squared a cosine omega t plus phi in general. And just plugging in the terms that we already know, we shall have minus 5.16 squared multiplied by 0.04, and then we have cosine 5.16 t plus 0. And so this gives us the expression that we want. So this would be 1.065, the negative in front of it, and we have cosine 5.16 t. So this is your expression for the maximum acceleration. Notice that the maximum acceleration, the amplitude 1.065 is our A max, and our maximum velocity V max was found to be 0.206, and that is our amplitude for the expression that we have for V of t. And our maximum amplitude for displacement is 4 centimeters, which we have in these functions also. So we've completed our example. So this is the end of our lecture for today. We shall continue next time with the energy of a simple harmonic oscillator.